Today we want to talk about capacitors, and this will be our second component we are investigating. Now, the capacitor is used to store energy, and the unit is the farad, denoted by the letter F. So what a capacitor is? Well, it is two metal plates with some insulating material in between them, also known as the dielectric. We can have any shape or any geometry as long as we fit that criteria. Now, there's two capacitors we're concerned with, the non-polarized and the polarized capacitors. With the non-polarized, it does not matter which way you put it into your circuit, it will function the same way. With the polarized capacitor, though, if we put it in backwards, this is what happens. Now, obviously, that's not good, and we want to avoid that at all costs. So we have two equations that we can find the capacitance with. The first one is epsilon A divided by D, where A is your cross-sectional area of the plates, D is the distance between them, and epsilon is the material characteristic. It's actually the permittivity of the material, which is really a material's ability to store an electric potential when it's exposed to an electric field. Now, the other equation for capacitance is the charge on the plates divided by the voltage applied to the plates. So before we move on to the displacement current, I really want to talk about the uniqueness of creating a capacitor. So we knew that with a resistor, our resistance was equal to the resistivity times the length over area. And even for a wire, which we model ideally as having zero resistance, in real life, we do have some length, we do have some area, and we do have some resistivity. So we are able to make a resistor simply out of a wire. Now with a capacitor, let's consider the following circuit. So we have a voltage source, a resistor, and we're just going to open circuit it. So if we look at this section here, well, what do we have there? We have wires again that are just stray, but those wires do have some area, so we know that exists. We know that there is a distance d between them, and we do know that we have air or the vacuum in between the wires. So we do have a permittivity, which is actually equal to the permittivity of free space. So we have all the criteria for a capacitor, which really shows that we can make a capacitor simply out of wires. So, although capacitors do have their own discrete components, they do exist everywhere in circuits. Okay, now we can talk about capacitors and displacement current. So let's consider the following circuit where we have a voltage source that goes to a switch. That switch goes to the resistor, and the resistor goes to the capacitor. The switch will close at time equals 0. This is easy enough to set up an experiment, so we can do that. So we have a power supply that's in series with our multimeter, that's in series with the resistor and the capacitor, and then back to the power supply. The multimeter will be acting as a switch. It'll also be measuring the current that's flowing through the circuit. Now, the strange thing is, when we connect this to the resistor, we notice that a current is being sensed and recorded. So the question really is, what's going on there? Now, it appears from that experiment that current is flowing through the circuit. But we know that we have an insulator between these capacitor plates, so that should be blocking all current. Well, what happens is when we have a time-varying voltage, we induce charge on one plate, and that causes electromagnetic effects through Maxwell's equations, which induce the charge on another plate to move. So if we look at a black box around the capacitor, and we can't see what's going on the inside, it would appear that we would have current going through the capacitor. But in all reality, we do not. We don't have any charge moving through the actual insulator. So what we do, we call this current the displacement current. Now, as electrical engineers, we really group the total current I as the electrical current that we are all aware of. And we also group it as the displacement current. So if we simulate this circuit after we close the switch and we have this at time just greater then t equals 0, what we have is we have some current that builds up some charge on the capacitor, and that charge is Q. So what happens is we have Q equals C times V. We know that the current is equal to dQ over dt, which is equal to C dV over dt. So this is the current that we are talking about as this I. As time reaches infinity, what happens is essentially this capacitor charges up to the point where the potential over the capacitor is the same as the potential over the source, so we have no current flowing. So similarly with resistors, we can find out what our equivalent capacitance is. So we know that if we had a switch and we closed that time equals 0, we would have some negative charge here, some positive charge here. We would have negative charge here and positive charge here, because we would have the electrons coming through, pushing the electrons here up, but they don't have anywhere to go, so they sit here, and then the electrons would actually go from there back to the source. And what we can say from this is that the charge on the first capacitor is equal to the charge on the second capacitor, which is equal to the total charge. So we can do a KVL around this loop, and what we can say is that V minus Q1 over C1 minus Q2 over C2 is equal to 0. Now, if we can combine these into one capacitor, we would have this circuit on the right doing another KVL loop around this. We can say that the voltage minus the total charge over the total capacitance is equal to 0. We can set these two equations equal to each other to arrive at Q1 over C1 plus Q2 over C2 is equal to QT over CT. We know that Q1 equals Q2, which equals the total charge, so we can really just divide by these and get rid of them all. And this says that 1 over the total capacitance is equal to 1 over C1 plus 1 over C2, which we can algebraically modify to say that CT, which is the total capacitance, is equal to 1 over C1 plus 1 over C2. So that is how we add or combined capacitors in series. Now with capacitors in parallel, we really need to look at this second equation. And how we get there is we know that current is equal to the change in charge over the change in time, which would be equal to the capacitance times the change in voltage over the change in time, assuming that our capacitor is constant. And what we do with this equation is we can say that the total current is equal to the first current plus the second current. That's just KCL at this node here. So we say that IT is equal to I1 plus I2. Well, from up here, we know that we can say IT is equal to C1 dV over dt plus C2 dV over dt. And because these are in parallel, we know that the voltage will be the same. Now we can look at this circuit here if we can combine them into one, and we can make a node right here. And what we can say is that I going in is equal to I going out, and this current here will be IT. So this is a very easy KCL, and we just say that IT is equal to CT dV over dt. Now again, we can set these two equations together to say that C1 dV over dt plus C2 dV over dt is equal to CT dV over dt. Or we can algebraically modify these again to say that C1 plus C2 dV over dt is equal to CT dV over dt. So we know that the total capacitance is just going to be equal to the sum of the capacitance. And this is similar to what we did with resistors. So if we look at how we did resistors for equivalent resistance, when we had series resistors, the total resistance was just the sum of the resistors. Now when we have parallel resistors, we had this equation. Inversely, when we have capacitors in series, we arrive at a similar equation to resistors in parallel. And when we have capacitors in parallel, we just add them together like we have resistors in series. Now this can kind of get confusing if you haven't seen capacitors before, but there's always a good old way to remember it, and we know that the equation for resistance is this, and the equation for capacitance is this. So if we have two resistors in series, separated by a distance d, what we can really do is set d, or the limit as d goes to 0. And what happens there is from 100 feet away, this starts to look like a resistor with just 2L for the length. So we know that the resistance has increased when we have resistors in series. Now for capacitors, when we have two capacitors in parallel, or many capacitors in parallel for that matter, we can now say that there is some distance L between them. And as the limit of L goes to 0, well, what really happens is from 100 feet away, it looks like these capacitors are touching, and the capacitance total area is 2A now, because we have this area and this area. So now the capacitance has increased. So when you have two resistors in series, the total resistance increases. When you have two capacitors in parallel, the total capacitance increases.